Hello everyone, welcome to my YouTube channel. Today I'm gonna show you how to analyze the data of EMG on Nordic Hamstring curl. Especially I'm gonna show you how to do filtering, rectifying, and enveloping the data. So goal of this YouTube video is to analyze the data of EMG. So the plot you're seeing is raw data of EMG. Pretty much it's really tough to analyze the data from just the raw data. By the way, this is EMG on right bicep femoris during the Nordic hamstring curl, and the y-axis is amplitude and x-axis is time in second. Then what I'm gonna show you is this later on. So I'm gonna do filtering, rectifying, and enveloping, and this is the plot you will see the end of the video. So by looking at this plot, you can see when the muscle action started, maybe like around here, and when it's ended. And as you can see, muscle is developing force until here, then it's dropping out. So you can analyze so many things with this plot, but in this video I'm just gonna show you how to make this plot from raw data. Then you may wondering, what do I mean by EMG on Nordic hamstring curl? I have a video to show you. So this is EMG. So or my classmate putting the EMG on our subject. So here is for semitendinosus and this is for bicep femoris. And we are using differential EMG, which means we have to put the two poles, and this big device is just the EMG transporter. So you get the EMG from here, two poles, and this device send the data to another device, and another device is connected to AD converter, and you see the waves, EMG waves on Pro EMG, which is the software. And yes, pretty much you can see the waves on the screen on the laptop. So that's EMG part. Then this is Nordic hamstring curl. So our subject is just going down, and yes, so this is what I mean. So this is EMG waves. So while he's laying down, his hamstring muscles are active. So the EMG detects the action potentials of the muscle or like hamstring. Then this is waves. Obviously the y-axis is amplitude and the x-axis is time, and actually you can see as time goes by, amplitude is getting higher. You may wonder why there is a plus and minus. It's actually because it's a waves, so like plus and minus is the same thing. So that's why later on we have to do the rectifying, but I will show you how to do that later on. So by this time you know what I mean by EMG on Nordic hamstring curl. So go back to the slide. Procedure. First of all, import the data, then detrain the data. So detrain means that find baseline. So sometimes EMG waves do not have baseline, which should be 0. Baseline sometimes like 1, 2, -1, -2. So we have to adjust the baseline by detrending the data. Then I'm gonna do power spectrum, filter the data, rectify the data. Then I'm gonna do moving average to make envelope. So I'm gonna show you how to do all those procedures by using Matlab. So let's go to Matlab. Okay, Matlab. So first of all, I have to import the data. So data is on my local computer, and I just imported into Matlab with Excel format. So pretty much, they said the software Pro EMG can provide EMG data with kind of any format. It could be CSV, Excel file. You just export it and download it, send it to whatever, like a USB or cloud, and you just download it into your local laptop device. Then you just import. Then I'm gonna save the data into variable called date. So so I'm just gonna run this. So this is the data. Let's take a look at the inside. Okay, so we did Nordic Hamstring curl 5 times. I'm gonna look at the first trial. So this is raw data. Sample is just data point 1, 2, 3. So we used 2000 sample frequencies. So 2000 data points. Sorry, 2000 data points represent 1 second. Then this column for right bicep femoris, and this one is for right semitendinosus and for left side. This is raw data. Then first of all, I'm gonna show you the raw data with plot. I'm gonna run this. Okay, so this is first trial. You are seeing right bicep femoris, right semitendinosus, and the left side. And this is y-axis in voltage, and this is x-axis, which is time in second, and this is raw data. You can see the second trial, third trial, fourth trial, fifth trial. So like I said on the presentation slide, it's really tough to analyze the data by just looking at raw data. So that's why I have to do some filtering, rectifying, enveloping, blah blah blah. But this is raw data. It's good practice to see raw data and how it looks. So that's why I did plotting raw data. So the function I used is stacked plot. Stacked plot is very useful to plot data in table format, because data is stored here is in table format. So if I just put the function here and input the data one by one in table format, stacked plot just create the plot like I showed you. But bad thing is it's not really flexible compared to just function plot, or you can make subplot basically, because this is subplot 1, 2, 3, 4. Stacked plot can create subplot automatically, but it's not really flexible. What do I mean that? So I just create y limits, because if I don't specify y limits like -2 to 2, the y-axis is just goes random or just adjusted by the function here, stacked plot. Then it's really tough to compare one another, so that's why I specify y limit, which is from -2 to 2, but then you lose y ticks. You only see 0. It's supposed to be here's 2 and here's -2, but you lose ticks. So it's really easy to plot in table format, but you lose ticks, and it's not really flexible compared to just plot and the subplot. So, but just if you just want to look at the raw data in table format, I think this is just enough. Then we can go to next step. Okay, next step is detrend the raw data. So as I explained, detrend means that you adjust the baseline to 0. So I'm gonna run this and you will see what I mean. Okay, so looks like it's not really different, because I think raw data is already adjusted to 0. So this one just look like raw data I showed you before, but actually detrended already. And this time I used the plot and subplot function, which is right here, subplot and plot right here. So you're seeing the ticks right here, 2, -2, and let's do the same. So y-axis is amplitude in both, and the x-axis is time in second. Right bicep femoris, right semitendinosus, and left side. And this is first trial, Nordic 1, Nordic 2, and etc. So the function I used is just detrend. You just input the data in detrend function. One thing you have to be careful is the data has to be matrix or vector at least. You cannot put table data here, so that's why I put a function called table to array. So this function converts table to matrix array. Then detrended data is saved in this variable. To make a plot, I just use a for loop. So this first for loop goes from Nordic Hamstring curl first trial to fifth trial, which means I make 5 prods right here. 1, 2, 3, 4, 5. Then another for loop because each trial has 4 muscles, right semitendinolis, right bicep femoris, and the left side. So this for loop goes from one muscle by one muscle. Then I specify the title. I specify y-axis, which is from -2 to 2. Then X label, which is just time in second. And subtitle is title for subprod. So there is a title here for subprod. This is title for all prod, but this is subtitle for just one subprod. And this is subtitle for subprod, and etc. Then y-axis or y label is a little bit tricky because this is common y label for all subprod. So what I did is just specify or extract the data for position in subprod 2 and subprod 3 and just combined and find height or like a middle height of subprod 2 and actually 3, yes, 2 and 3, yes. Then use axis function position. This is input argument, and here it should be x-axis minimum, x-axis maximum, y-axis minimum, y-axis maximum, and visible off. Then you put y label as usual. Then I get this y label, like common label. So I specify the position for prod 2 and 3. If you do prod 1 and 2, y-axis moves right here in this code. So we just did detrend, so we can go to the next step, which is power spectrum. Okay, so next step is power spectrum. So I'm gonna apply power spectrum muscle by muscle and trial by trial. So that's why I put for loop. The first for loop, the I goes from 1 to 5 because I have 5 trials, and the second for loop goes muscle by muscle. I mean, this for loop, the principle is same as the subprod and the prod here. So it just goes from one muscle and muscle, one muscle, one muscle, and first for loop goes one trial, one trial, one trial. Then I just put detrain the data right here and save it to mat, muscle by muscle. Then the mat goes to here inside of the function called p spectrum, and output function of this function is power and frequency. And same thing, I'm gonna do subprod and prod. X-axis is frequency and y-axis is power. So I just put power to decibel function, so power is converted to decibel. Then same thing, title, and just common y label here, put subtitle for each subprod, and x label is frequency this time, not time, it's frequency. So let's run this. Okay, so this is power spectrum. As I say, I'm sorry, y-axis is decibel and x-axis is frequency. So as far as I can see from this prod is frequency band is something from here to here. I think the rest of the waves or frequencies are synchronize. So common practice of filtering or common filtering routine for EMG is between 20 and 500 frequency, band pass frequency. So what I want for frequency is between around from here to here, or like even here actually. Then I'm gonna get rid of rest of the frequencies, which could be noise. We cannot remove the noise completely, but we can try to avoid the noise as much as possible. And just by looking at power spectrum, we can see which one is EMG frequencies and which one is noise frequencies. Yes, so pretty much the same, I think, from 20 to 500 EMG signal. So Then we can go to the next step. Okay, so next step is filter the data. So first one is just sample frequencies. So I use the 2000 sample frequencies, so I just put 2000 right here, and I use a function called butter. So the first input argument is order, so I just use second order. On EMG, the common practice is second or fourth order, what the number represents. So as I mentioned on power spectrum section, I want frequencies between 10 and 500, or I said 20, but it's fine. It's a little bit subjective, but 10 or 20 is fine for lower boundary, and the higher boundary I just say 500. Then actually there is a transition between included frequency and excluded frequency, and this order defines how sharp or how smooth the transition. So if you put higher value or higher value order here, you get sharper slope between included frequency and excluded frequency. It kind of depends on what you want, but for EMG, second order, fourth order is kind of like safe zone. You never be wrong if you put 2 or 4, I would say. Then I put lower boundary and higher boundary like I said, but I have to do some divisions, which is half of the frequency. So in this time 1000, so 10 divided by 1000, and you get the frequency you want to cut off for lower boundary. So anything less than 10 and anything higher than 500 frequency, just exclude it, and that's band past that. So if you want to do low pass or high pass, you just change the argument right here and change the cutoff frequency right here. Or you can use notch, which is you defined lower boundary, higher boundary, and the filter includes everything outside of the bandpass. And the butter function output coefficients which are needed in field function. So this is common practice. You use Butterworth or butter function with field function. So field function is double order, which means like you filter in forward and backward. Reason why I have to do 2 order like field is because if you just filter in forward direction, it creates some delay. Like the sine wave is like this, then you wanna filter something, and if you just do filtering in forward, the sine wave moves to the right a little bit. To prevent that, I have to do field, which is 2 ways filtering. So one way is in forward and the second way is backward. Then I can prevent the delay. So you just put coefficient created by butter function B and A. So you just put it, and the third input argument is just a data. So I use a D-trend data for field function. Then output is just filter data. Then I saved all filter data right here. Then plot is the same. So I'm just gonna run this. So maybe it's really tough to see the difference between filter data and raw data, but I would say the data is a little bit fine, or maybe the data didn't really have noise. But anyway, this is filter data and it doesn't look like the plot I showed you on the slide. But yes, pretty much this is filtering, and the next step is rectifying. So let's go to the next step. Okay, so the next step is rectify the filter data. I mean, rectify is actually the fancy word, but it's not really difficult to do that because I just need to flip the sign from negative to positive. I just use a function called abs. So the function just flip the sign, like I said, from negative to positive, and I just run this and you will see what I mean. So this is what I mean. So the plot I showed you before had negative values, but I just flipped the sign from negative to positive, so the data is all positive right now. So that's what I mean, and that's pretty much the rectifying. So the last step is moving average, and that creates envelope. So let's go to the next step. Okay, so the last step is apply moving average. So moving average is just averaging certain sequence. So let's say I'm gonna do moving average of 10, which means I'm gonna find mean of 10 sequence, like let's say 1 1 1 1 1 1 1 1 1. That's a 10 sequence of 1, and I'm gonna find average of 10 1s. Then obviously that's 1, so the first data is 1. Then I move one number to the right, so I'm gonna do the same thing, find the average of 10 sequence. So first 9 is 1, but the moving average introduces one extra number, which is 11th data. You know what? I'm gonna show you the data, and I will show you what I mean. So first 10 data, and I'm gonna find average and put average data in the first position, like let's say right here. Then I'm gonna do like another moving average. So the next 10 sequence from here, like 2 to 11. Then I'm gonna find average and put the data right here, and move one sequence or one data point right here, and do the average of next 10 sequence, and put the average data right here, and do the same thing, do the same thing, do the same thing until the end. And like I said in the filter section, this is just only forward way. So after forward way, I have to do backward, because like I said, if I only do forward, it introduces delay of the data, so I have to do backward to prevent the delay. So that's what moving average does. Then the function is very simple, just move mean. You just put the data, and you define moving average. I said 10 for example last time, but I put 2000, which means 1 second. If you remember, I said 2000 sample frequencies, which means that 2000 data points represent 1 second. So I'm gonna do moving average of 1 second basically. And I put 1 because the data is in column wise, not row wise. If you wanna do moving average in row wise, you have to put 2 right here. Then basically the same thing, just plot the data I just stored right here. So I'm gonna show you the plot. Okay, so this is a plot I showed you on the presentation slide. So you will see the force development right here, and probably ended up right here, and it goes down, goes down, goes down. Yes, now you see when the muscle force started and probably when muscle force finished. So on the raw data plot, you couldn't really see when the muscle force started and when the muscle force ended, or even like force development. You kind of see force development, but like not as clear as this plot. So pretty much this is it for this video, and by using this plot you can do so many things. Like I say, you can find the muscle on and the muscle off and the muscle development, and you can compare the force between this muscle and this muscle, or just the right and the left. And you can compare the muscles in amplitude wise or frequency wise, but I'm not gonna show you those comparisons or detection of like a muscle on off or force development, not this time, but I promise I'm gonna make a video to compare those muscles or detect muscle on and off. So see you next time.